The physics topic in this video tutorial is all about elastic properties of matter. So my dear students, stick around, watch and learn. Consider a material with a certain length and a cross-sectional area, and it is subjected to a force whose direction is directed outward, perpendicular to the cross-sectional area. What's going to happen to this material? Alright, so the amount of force over a unit area, in this particular illustration, is defined as tensile stress. Our symbol for tensile stress is the Greek letter sigma. So tensile stress is equal to the amount of force F divided by the cross-sectional area. There is also an opposite kind of stress, and this is what we call compressive stress, which is exactly the opposite of tensile stress. As shown in this diagram, the direction of the applied force is inward, perpendicular to the cross-sectional area. But the formula for compressive stress is just the same as the formula for tensile stress. Tensile stress, in general, is the stress state leading to expansion. That is, the length of a material tends to increase in the tensile direction. Compressive stress is just the opposite of tensile stress. Tensile stress or compressive stress, denoted by sigma, is equal to F over A. And sigma is expressed in Pascal, which is the SI unit for stress, while the force F is expressed in Newton and the cross-sectional area is expressed in meters squared. There is another kind of stress wherein the direction of the applied force is along the direction of the plane of the cross-sectional area. Alright? And we call this kind of stress as shear stress. Okay? The direction of F is such that it is not perpendicular to the area, right? But rather it is along the plane of that surface area. Moreover, we say that a shear stress between two objects occurs when a force pulls the object along the same plane as the face of the object, abutting another object, in other words, touching. another object adjacent to it that is being pulled in the opposite direction as indicated in this drawing. Similarly, shear stress within an object will occur when a force parallel to the plane causes one plane of the material to want to slip against another, thus deforming the material, as shown in the second illustration or diagram. Okay, the original shape is as shown by the broken line, all right? And when the force is applied, okay, along that surface, all right, along that surface, which causes a change in the displacement labeled here as delta L, all right? So delta L represents the displacement, horizontal displacement that results from the application of the force F without changing, all right, or without causing any displacement on the opposite surface down here, right? So if you're going to divide the amount of force F, okay, by the area, the surface area of this particular uh, what we call side, okay, then we are defining this kind of stress known as shear stress. A very important elastic property of all solid materials is known as Young's elastic modulus, labeled here by capital letter Y. So, when you say Young's elastic modulus, we are just expressing the ratio of the amount of stress over the amount of strain. Okay? So, when you say strain, we are referring to the ratio of the change in the length over the original length of an elongated material. This is particularly true for uh, a kind of stress known as tensile or compressive stress. So, if the kind of stress is tensile or compressive stress, the corresponding kind of strain is also known as tensile or compressive strain, right? If we are going to represent tensile stress with the Greek letter sigma, all right, and tensile strain being equal to delta L over the original length, or delta L divided by L naught, then we come up with a formula for Young's elastic modulus, capital Y, okay? So by transposing the L naught, okay, placing L naught in the numerator, we will come up with a direct working equation for Young's elastic modulus, capital Y, being equal to the product of the applied force F and the original length L naught divided by the product of the cross-sectional area, capital A, and the change in length, delta L. So that's true well for any kind of tensile stress or compressive stress, as shown in these drawings. The meaning of each quantity in this formula is defined here. Capital F represents the applied force, which in SI system is normally expressed in Newton. while the L naught, or the initial or original length of the rod, is expressed in meter. Change in length delta L, which is just the difference between the final length and the original length, okay, more commonly known as change in length, is also expressed in meter. Which means that the unit SI unit for Young's elastic modulus Y is Pascal, which is also equal to Newton per meter squared. For shear stress, all right, any shear stress that causes a body to undergo what we call shear strain, okay, shear stress divided by shear strain is what we call shear modulus, denoted by capital letter G. So shear stress or shear modulus can also be expressed in terms of the ratio of the shear strain gamma. Okay, when you say shear strain gamma, it's just equal to the displacement delta x shown in this illustration divided by the what we call the original length. All right, if you measure this side of the polygon, all right, from this side to the other side beneath it, then letter L stands for that what we call original length. All right, but when subjected to a parallel force F, parallel to the surface, the top surface that is, then we are talking about shear strain, which can be denoted also by a Greek letter gamma, and that is equal to delta x, or the change in the displacement divided by the original length L. So dividing the shear stress by the shear strain, then we come up with the formula for the shear modulus capital G, right? The applied force F divided by the area of that particular surface gives us the value for the shear stress. And then if you divide it by the shear strain represented by gamma, then we come up with the formula for shear modulus capital G, right? And that is simply equal to the product of the force applied F times the original length L divided by the surface area capital A and the change in the displacement delta x. Capital A here means the area on which the force is applied, parallel. All right, the force has to be parallel to the area. Delta x is the displacement of the body, all right, along the horizontal, labeled as delta x, while capital L, of course, is the original length. When the object has a perfect cube shape, all right, then the L is just equal to the one side of the cube, isn't it? But in here, we are using capital L to represent that side of the polygon. So it can either be a parallelogram, all right, or a cube. Doesn't matter as long as our definition for L is as shown in this diagram. All right. The change in delta x makes an angle theta, all right, from the vertical line to the new length, all right. If you're going to divide that delta x over the adjacent side of the angle L, then we are defining tangent of the angle theta. And that is simply equal to what we call shear strain gamma. Delta x divided by delta L, okay, mathematically can be expressed as tangent of the angle theta in this drawing. What happens if an object is subjected to a changing pressure delta P and causes the volume of the object to also change as shown in this diagram? Okay, if you are going to divide the amount of the change in the pressure, okay, by the ratio of the change in the volume delta V to the original volume V, then we are defining another kind of modulus. We call it the bulk modulus, denoted by capital letter B. Okay, so P stands for pressure, V is volume, where the letter capital B denotes what we call bulk modulus, just like the two first kinds of moduli, Young's modulus as well as shear modulus. Bulk modulus is also expressed in SI unit. It is expressed in Pascal or Newton per meter squared. Okay. The corresponding change in pressure delta P, all right, has its SI unit also in Pascal. All right. While the change in the volume delta V is expressed also in the SI system, the unit is meter cube. And since based on the formula for bulk modulus, change in volume delta V divided by the original volume V, all right, the corresponding strain, right, or we call it volumetric strain, will have no specific unit because the unit for delta V and the unit for V simply cancels out. That's the reason why the unit for the bulk modulus capital B is the same as the unit for what we call uh, volumetric stress, denoted by delta P. So to summarize the three kinds of moduli that we have discussed, for Young's modulus, we say capital Y is equal to tensile stress divided by tensile strain. That goes through also for what we call compressive stress. The corresponding strain is known as compressive strain. For shear modulus, all right, capital G is just the ratio of the shear stress to the shear strain. And For our last type of modulus, capital B is equal to the volumetric stress, that is delta P, divided by the volumetric strain, delta V over V. For our first question, number 1, a copper wire is found to break when subjected to minimum tension of 36 newtons. If the wire diameter were half as great, we would expect the wire to break when subjected to a minimum tension of, letter A, 9.0 newton, letter B, 18 newtons, letter C, 36 newton, or is it letter D, 108 newton? Our answer, since the tension F is inversely proportional to the cross-sectional area, where area is equal to pi r squared, if the diameter is half as great, then the tension is decreased to 1/4 the original value, or 1/4 of 36 newtons, which gives us 9.0 newtons. So the correct answer to this question is, of course, letter A, 9.0 newton. For our second question, question number 2, a 5,000 Newton force compresses a steel block by 0.0025 centimeters. How much force would be needed to compress the block by 0.0125 centimeters? Is it letter A, 1,000 Newton, or letter B, 2,500 Newton, or letter C, 5,000 Newtons, or is it letter D, 25,000 Newton? So our answer and explanation, since the compression F is also directly proportional to the change in length or elongation delta L. If the delta L is increased by a factor of 5, why a factor of 5? Because from the original value of 0.0025 will make it 0.0125 centimeters. So that's an increase of a factor of 5. So if delta L is increased by a factor of 5, the tension is also increased to 5 times the original value, or 5 times 5,000 Newton, which is 25,000 Newton. So our answer to this question is letter D, 25,000 Newton. Question number 3. A cable is 100-meter long and has a cross-sectional area of 1.0 millimeters squared. A 1,000 Newton force is applied to stretch the cable. The elastic modulus for the cable is 1.0 raised to the 11th power Newton per meter squared. Question is, how far does it stretch? Is it letter A, 0.01 meter, B, 0.10 meter, letter C, 1.0 meter, or is it letter D, 10 meters? So our solution to this question, using the formula for Young's elastic modulus, capital Y, is equal to F L naught divided by capital A multiplied by delta L. we are going to come up with a working equation in finding the change in length or elongation, delta L, right? Because the question which says how far does the cable stretch, okay? The question implies that we are going to determine the change in the length or elongation, all right? Given the original length of the cable, which is 100 meters, the cross-sectional area of 1.0 millimeters squared, and the value of elastic modulus, capital Y, is also given. So, substituting to our formula for delta L, we have the amount of applied force, which is 1000 Newton, multiplied by the length of the cable or original length L0, 100 meters, divided by the cross-sectional area, which is already converted to meters squared. So 1.0 millimeter squared is just the same as 1.0 times 10 to the negative 6 meter squared. And that area is to be multiplied to the value of Young's elastic modulus, which is 1 raised to the 11th power Newton per meter squared. In doing our math, we will come up with the value for the elongation or change in length delta L equal to 1.0 meter. So our answer to the question, of course, is letter C, 1.0 meter. Question number 4. A shear force of 400 Newton is applied to one face of an aluminum cube with sides of 30 centimeters. What is the resulting relative displacement? The shear modulus for aluminum is given as 2.5 raised to the 10th power Newton per meter squared. Choices are letter A, 1.9 raised to the negative 8 meters. Letter B, 4.4 raised to the negative 8 meters. Letter C, 5.3 raised to the negative 8 meters. Or letter D, 8.2 times 10 to the negative 8 meters. Okay, our solution and answer, okay, from the formula of shear modulus capital G, which is equal to shear stress, F divided by A, divided by the, what we call shear strain gamma, that is simplified as the product of force F times the length L divided by the area and delta X. But since we are looking for the relative displacement or delta X, then there is a need for us to transpose the equation for determining delta X. And that will be equal to delta X is equal to FL divided by A capital G. And when we substitute the given quantities, we have 400 newtons for the applied force, 0.30 meters for the original length, capital L, divided by the surface area of one side, which is 9.0 raised to the negative 2 meters squared. All right. Originally, what was given only is the side, okay, the measurement of one side of the cube equal to 30 centimeters. So when converted to area and using meters squared as the unit for area, then that is equal to 9.0 times 10 to the negative 2 power meters squared. And then that will be multiplied by what we call the shear modulus for aluminum, which is given as 2.5 raised to the 10th power Newton per meter squared. As usual, doing our math with all the units expressed in the SI system, we will arrive at the value for the relative displacement delta x, which is equal to 5.3 raised to the negative 8 power meter. In other words, our answer to the question is letter C, 5.3 raised to the negative 8 meters. And finally, we are in our last question, question number 5. At a depth of about 1,030 meters in the sea, the pressure has increased by 100 atmospheres. That is equal to about 10 raised to the 7 pascals or Newton per meter squared. Question is, by how much has 1.0 meter cube of water been compressed by this pressure? Given that the bulk modulus of water is 2.3 raised to the 9th power Newton per meter squared. Choices are letter A, 2.3 raised to the negative 3 meter cube, letter B, 3.3 raised to the negative 3 meter cube, letter C, 4.3 raised to the negative 3 meter cube, or letter D, 5.3 times 10 to the negative 3 power meter cube. So, our solution and answer, okay, based from the equation of bulk modulus, capital B, which is equal to the original volume, right? The original volume, capital V, multiplied by the change in the pressure or the volumetric stress, delta P, divided by the change in the volume, delta V. Since we're looking for the change in the volume, all right, delta V, the working formula for that is delta B equals original volume V multiplied by delta P divided by the bulk modulus. And as usual, substituting the given quantities for that formula. Okay, the original volume is 1.0 meter cube multiplied by the volumetric stress or delta P, 10 raised to the 7th power Newton per meter squared, divided by the bulk modulus, capital B, or 2.3 raised to the 9th power Newton per meter squared. Solving for delta V, what we get is delta V, or the change in the volume, equals 4.3 times 10 to the negative 3 power meter cube. In other words, the answer to question number 5 is letter C. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.